Good to see you all. Hope everything's going well. And yeah, so the plan for today is to continue talking about discrete random variables that we started talking about last time. I've got like stars around my head. Hold on a second. Okay. So before we get started, I just want to let you know that originally the homework for this week was set to be due on Thursday. I realized that most of that stuff we're actually not going to get to until today. So the plan was eventually to have homeworks due on Mondays at midnight. So that's going to be the plan. So this homework, I originally had it up as due on Thursday of this week, but it's been pushed back to Monday of next week. And it's going to mostly be on what we talk about today. So you should be able to get going on it. Otherwise, hopefully you're getting kind of used to the flow of assignments, quizzes being due before class. Now homeworks will be due on Mondays. But any questions about that or anything else for that matter? Everyone's able to get the materials, find everything where you think it should be. That's all working out well. Okay. So hopefully you guys also were able to get R and RStudio installed on your computers. We're going to be using that today, basically as like a calculator at this point. But really quickly in a week or so, we're going to be doing more advanced stuff in R. So I definitely want to make sure that is up and working, and about half of your homework assignment is going to be using R as well. So that'll give you a good opportunity to make sure that R is installed and functioning well for you. Okay, so if there aren't any questions, then let's pick up with where we left things off last time. So this is what I called worksheet 3A. It's kind of the first part on discrete random variables. So just to kind of back up for a second, the first thing is, what is a random variable? It's actually not random or a variable, really. It's a map from the full sample space of experiment into real numbers. So we've been working with discrete random variables because we've been counting things like how many questions did you get right on a quiz, or how many batteries in a shipment were good. And then we talked about probability distributions last time, and we kind of ended thinking about some of these properties on this page. And so kind of the key here is this notation, f of x is what's called the probability distribution, or oftentimes called the probability mass function or probability distribution function. And so it tells us what is the probability of getting exactly X successes in an experiment. Whereas when we talk about the cumulative distribution function, this is telling us what is the probability of getting at most X. So this would be everything up to and including X. And we kind of ended last time talking about some properties that the probability distribution would need to satisfy, as well as the cumulative distribution. So any questions about where we left things last time? Okay, so then I want to talk about a couple of measurements that we can take for a random variable. So one of which is what's called the expected value. The other is what is called the variance. And so we'll be dealing with both of these things quite a bit this semester. So the expected value of a random variable is by definition equal, we denote it with the Greek letter mu, first of all. That's what this letter here is representing. And we calculate it if we're working with a discrete random variable by saying, what are the possible values of the random variable times what is the probability that we would get that value, and then we sum up all of those products to calculate what's called the expected value. So I'm gonna kind of come back to point 4 in a second. But let's say we're gonna think about question number 5. And so for this random variable, we're gonna calculate the expected value and the variance of this random variable. So the idea here is there's a charity, they're running a raffle as a fundraiser. And so there are certain prizes that you can get. You can get $500 prize, you can get a $100 prize, or you can get a $20 prize, or perhaps you can get nothing at all. So what we'd like to set up here is what are the possible outcomes in this sample space, and then how likely are each of those outcomes to occur. So for example, here with the raffle, right, it's possible that somebody doesn't win any money. It's possible that they win $20. It's possible that they win $100, and it's possible that they win $500. Right, and that's the whole possibility that would give us all of the possibilities for the random variable here. And then we can go ahead and calculate what is the probability that each of those things would happen. So we're going to sell 1,000 tickets. And what we see is that there's one grand prize of $500. So in other words, what would be the odds of winning $500?
One in 1,000.
Yeah, so that's going to be 1 in 1,000. So we can write that as a decimal as a 0.001. And then we can say we've got 2 second prizes, again, out of the 1,000 tickets. So that would be 2 out of 1,000, right, which we can write as that. And for $20, we've got 10 of those. So that would be 10 out of 1,000. And then all of the rest would be not winners, right? So doing the math here, that would give us the remaining are 987 losing tickets out of the 1,000. Yes, Max.
I was just wondering if this would be seen as an independent or a dependent problem, just because how they pick it, you know, they would pick one person out of it, but they wouldn't be re-entering that person for the other prizes, right?
So yeah, I think you're kind of thinking a little bit about like, is this like a binomial distribution type of thing?
Oh, I'm not talking about it in terms of that. I was just curious whether it would be seen as dependent or independent.
So you would need to compare 2 different events to determine whether they're independent or not.
Okay.
So here we just have like one event we're thinking of, like, are you going to win? So we would need to kind of compare 2 different things to think about them being independent. So we're only picking one card out of here. Yeah.
Gotcha. So I was thinking of it as, you know, the chances of getting the first, second, third as well, not just win or lose. Got it.
Yeah. Yeah, that's a total different thing that we'll talk about later today. Like, what are the odds that nobody wins until the 4th ticket is picked or something like that? Is a little bit more complicated. Yeah. Okay. So any questions about how we completed this table over here? So this would be what we have random variable X. And we would call this the probability distribution, this table being the probability distribution for that random variable. Okay, it's just a map that says for each outcome, how likely is it to occur? And so if we wanted to calculate the expected value, again, which we can also write with mu, practically speaking, this is going to tell us how much should a person expect to win if they buy a ticket? Which is equivalent to saying, on average, how much does a ticket win? So this average and expected value can be used interchangeably in this sense. And how we can calculate this using the definition so we're going to sum over all possible values of x. What are the possible outcomes and how likely are each of those outcomes? So in this case, we have this table that's up here. So we would have like one outcome is 0 and its odds of happening are quite likely. That's the most likely thing. So the kind of practicality of what we're doing here is we're saying, how much money can you win times how likely are you to win that much money? And then we're going to add all these up. So the other one was 100. And then it was 500. And adding all of that up, I'll do the math, winds up being 90 cents. So you buy a ticket, you should expect to win 90 cents. Keep in mind that I think you purchased that ticket for $2. So this is good to know if you're running the raffle and you have a charity or you have a foundation and you're trying to raise money for this charity, you would want to make sure you charge at least 90 cents per ticket, right? To break even. But then you can calculate how much you want to charge for ticket based on how much money are you hoping to win, taking into account how much you know you're going to have to pay. So we would say, so that's the expected value. And what's really important to note here is that like nobody's actually going to win 90 cents for a ticket, right? You're either going to get 0, whatever the options were. So this isn't telling you like what any one person is actually going to get. It's telling you on average, how much are people supposed to win? But again, you know, if you buy one ticket, you have no chance of winning 90 cents. So the expected value doesn't have to be one of the possible outcomes, and that's important to note. Any questions about how to calculate it or what it actually is telling us? Okay. So next we'll calculate the variance for this example. But before we do that, let's kind of do this. Let's prove a general property. So by definition, here's how we calculate the variance of a random variable. And I'd like to show that that calculation above is equivalent to this kind of what we'll call like a shortcut down below. So let's kind of prove this result for a discrete case, and we'll see that it'll follow similarly for continuous random variables next time. But we're going to calculate the variance of x in general. And again, We denote the variance oftentimes with the Greek letter sigma, lowercase sigma squared. So just be aware that this notation and this notation, they might get used interchangeably. And so by definition, we should calculate this. But I'm going to do a little bit of algebra inside of here. By just distributing the x minus mu squared. And I should say that in this formula, right, this mu, right, would be the expected value that you calculate. So in order to calculate the variance, you need to first know what the expected value is. The variance depends on the expected value. So all I've done so far is just a little bit of algebra, right? Just squared that expression. And now I'm going to distribute this probability to each of those three terms. Okay, are there any questions yet about this?
Why did you move the x that was below the z, or the summation sign? Sorry.
Yeah, they're still there. You're right.
Okay.
I was just kind of
Going fast.
just lazy. Yes, maybe lazy is a better word. Yeah. So that's telling us that we're summing over all of the possible values of random variable x. So this first piece over here, this would just be the expected value of x squared, right? Instead of having an x in here, we have an x squared down below. So this would be equivalent to saying this piece over here is just the expected value, not of x, but of x squared. On this piece over here, keep in mind, this mu is a constant, right? It doesn't depend on x. So just like I could pull the 2 out from the sum, I could pull the mu out from the sum. So what would be left if I pull that out? Is this expression right here is just the expected value again, right? The sum of x times the probability of x is exactly the expected value. So we're going to get a minus 2 mu, and then all of this stuff over here is the expected value. So it is another mu. And for the last piece, this is constant as well, so that could come out. But we still have to deal with the sum of all of the probabilities. And remember, when we have a probability distribution, if we sum the probabilities over all of the possible outcomes x, we saw last time, right, that all of these probabilities should add up to 1 because they need to exhaust the full sample space. So this means we have an expected value of x squared. From the red stuff, we get minus a 2 mu squared. And then from the blue stuff, we get 1 times mu squared. So in other words, we get a plus mu squared. And then we can take the minus 2 mu squared and add it to the plus 1 mu squared. And this gives us e to the x squared minus mu squared, which is exactly what we were hoping to get up here. Okay, so in any case, here's a nice shortcut that we can use. So I did want to kind of just justify it. If you have any questions about the justification, maybe I'll just ask you to kind of stick around after class, since I don't want to focus as much on the proof technique here, but more so the using the result. But just to back up, like, what is this actually calculating the variance? It's telling us what is the expected value of the difference of a value x from the mean of that whole random variable. So in some sense, this is telling us on average, like how far away are the values of x from the average value. We'll kind of interpret this a little bit more carefully, but you can think of so it's kind of telling us what is the expected distance of a value x from the mean value of x. So it's telling us how spread out the values are.
Isn't that just the same thing as the standard deviation?
The square root of the variance is the standard deviation. Yes. So the
Okay.
variance is the standard deviation squared. So when you find the standard deviation, usually you find the variance and then you take the square root of the variance.
Okay.
Yeah, and we'll get much more into calculating these and what they actually tell us. So in this case, for the charity raffle, it'd be telling us, like, on average, what's the difference that I should expect to win? How far is that going to be from the average, which is 90 cents? So are most tickets going to win about 90 cents, or are most tickets going to win vastly different stuff from 90 cents, which we see most of the tickets here are actually going to win something pretty close to 90 cents. Most of them are going to win no money. And there's only going to be a few tickets that do win some money, but the money you win is quite different from 90. So in some sense, we do have some spread of values here. And so if we want to calculate the variance, here's a nice kind of useful tool for this. So we had 0, 20, 100, and 500. And these were, that was the probability distribution that we found. And so if we want to calculate the variance of this, then again, technically, we're calculating the expected value of this. Which we just showed is equal to that. And we already found the expected value. That was 90 cents. So I can fill that part in. And what's left is to figure out, well, what is the expected value of x squared? So I think I did my squaring correctly here. So if we square each of those values of x, then we would get the following. And so when we calculate the expected value of x, we summed up x times the probability that x occurs. If I want to calculate the probability, or excuse me, the expected value of x squared, then we have a 2 here. So rather than just have an x there, we would take what is the value of x squared times the probability that x would occur. So one way that you can, if you're organizing your thoughts in a table, is rather than say x times p of x plus this one times that plus this one times that, we're going to take x squared times p of x and then x squared times that one. So you can do all these calculations separately in a table if that's how you like to group them. And then if you add up all of those values, I don't know if anyone has done it. I'm having Excel do it for me. I'm getting 274 when I add this up. So that's telling me what's the expected value of the squared of the winning, which is not all that helpful here, but it is a piece that I would need to calculate the variance. So altogether, the variance would therefore come out to $273.19. Any questions? You've got a homework problem that's going to have you go through a similar calculation, like losses for an insurance company type of thing. If you were interested in calculating the standard deviation, that would just be denoted with a sigma. You might denote that with an SD. And we would just take the square root of the variance. Which is like $16.53. So this is telling you like on average, tickets vary from 90 cents by an average of like $16.53. It's telling you on average how far away are the winnings from the average amount of winnings that you should expect. So it's telling us how spread out our values are is the simplest way to explain the standard deviation. So we've talked about random variables. We've talked about their probability distribution, their properties that it must satisfy, the cumulative distribution function properties that it must satisfy. And now two very important measurements of a random variable, which are the mean, the expected value, and the variance. So one is going to tell us kind of where the data is centered, which is the mean, and the other is going to tell us how spread out are the values, and that's going to be the standard deviation. Okay, no, if there aren't any questions, I'll give you guys a chance, then we'll move on to the next worksheet. But any last thoughts or questions? Okay, so then let's now take a look at some very special types of discrete random variables that come up a lot that we'll be working with this semester. So the first of which is binomial distribution. And so here again, we're talking about discrete random variables. So we're in chapter 2. And so these are going to be a map from the sample space. Okay, usually we would say into the real numbers, but when we're dealing with discrete random variables, the outputs here are going to be things like 0, 1, 2, or some subset of that, right? Since we're counting things. So for example, this example with the lithium batteries that was in the video that we've been talking about, this is an example of binomial distribution. And again, the kind of three conditions that we need to check in order to have a binomial distribution are that, first of all, we have like a fixed number of trials. So we can think about each battery that's being sent in this shipment as a trial. And we are sending out 10 batteries. So we've got our number of trials would be 10 in this case. Okay, each trial has two possible outcomes. Right, a success or a failure, which is the case here, right? A battery is either defective or it isn't defective. And that's where the binomial part of the binomial distribution comes in. So it's a very binary thing. Either we're going to add to our count or we're not going to add to our count of successes. Right, and then the last kind of point here is each trial is independent of the other. That means whether or not trial 1 is a success or a failure doesn't affect whether trial 2 is a success or a failure, and so on. So we let n kind of denote the number of trials. We would let p denote how likely are you to get a success in any one trial. And so here, we are defining X as the number of good batteries. Whoa. So the probability of a success would be how likely are we to get a good battery, which is 99% of the time. And so we use Q to denote the probability of failure. So this notation is pretty standard across, all textbooks and all software, N, P, and Q, for binomial distributions. And so R is going to be really good tool to help us calculate these, but let's kind of make sure, like, what do we look for in order to know what to put into R, and why does R calculate things the way it does? So if you want to calculate the probability of getting this particular outcome over here, which happens to have X equal to 8 good batteries, we can use the fact that these are all independent events. So this is equal to P to the G times the probability of a bad battery squared. Right? That's the independence. We can just multiply these out. So this would give us the 0.99 to the 8th times the 0.01 squared. That's really small. I'm going to lose count of zeros. I think there's comes out to that. Okay. Any questions about that? And so I think on the quiz, you had to do some things like, how likely are you that you would get like no questions right, or all 3 questions right, and things like this. If I want to calculate this, which is telling us what is the probability of getting exactly 8 good batteries. It's not going to equal this, right? Because there are other ways that you could have gotten a shipment of 8 good batteries, right? It doesn't have to be the first 8 were good and the last 2 were defective. It could be that the first 2 were defective and the last 8 were good. And there's all other sorts of ways that we can fit, say, like 8 Gs into a string of 10 letters. So if we want to calculate how many different ways can we get exactly 2 out of 10 batteries defective, okay? Or we can think about, 8 out of 10 batteries that are not defective. But how many different ways can this occur? And we know how we could count up those.
Would it be n choose k?
Yeah, that's exactly right. So we're trying to think of, we have 10 places to put things. How many different ways can I put, 2 Ds and 8 Gs arranged into a string of 10 things? So we have 10 things. And here, what we're actually trying to do is, let me kind of just change this. Instead of saying 2 out of 10 batteries defective, we're going to say 8 out of 10 batteries are good, okay, are not defective, because we're thinking about the success here is a good battery. So we're going to think about, out of 10 places, how many ways can we fit 8 different things? And remember, this is equal to 10 factorial over 8 factorial times 8 minus 2 factorial. So if I want to calculate how many ways, or what is the probability that exactly 8 good batteries get sent, there's kind of 2 things that I need to think about. First of all is, how likely is it that we would get any one shipment of 8 good batteries? And that's what we calculated up here. And the next thing to think about would be, how many different ways can we accomplish that? And that's what we get from this. And the probability that we get 8 Gs and 2 Ds would be the same, right, in each of the, no matter how we order them, since we get them with a product. So altogether, we could calculate this without using technology. Using a formula that looks like this. So you can think about this formula in two parts. This is relating to how likely are we to get 8 good in 10 batteries. And then this piece over here is telling us how many different ways can you do that. So we would need to add all of those up. So that comes out, calculating that to 0.004. Just so you know, this over here winds up being 45. So that is a result of taking the 45 different ways that we could arrange 8 good batteries in a shipment of 10 times the probability that any one of those things would happen. So generally speaking, the formula would look like this, where N is the number of outcomes, or is the number of trials, excuse me. So N is representing the number of trials that we have altogether. S is denoting how many successes we are looking for. In this case, N was 10. We wanted to say how likely are we to get exactly 8 successes. And P and Q are denoting probabilities of success and failure. And so since these factorial or these combinatoric calculations are time consuming, it's nice to have some technology that's going to do that for us. But you should be prepared to think and explain to me or somebody else, like, why does this formula make sense? Like, what does this thing represent in the formula, and so on. So you should be able to kind of make sense out of the different components of this formula. Okay, any questions? Okay, so let me open up R for you guys. So if you've got R handy, we can check it out to see if it's working. I'm going to share my full screen here. So sorry, you might see yourselves embedded inside of yourselves in a second. Can you see like my full screen here? Yep. So yeah, so at the bottom, I've got a whole bunch of stuff that I use, one of which is RStudio. So wherever you've got RStudio, I've got a Mac, obviously, but should look pretty similar icon if you have a PC. If you've installed R and RStudio, when you open up RStudio, it's going to have R running in the background automatically. So I just click on that, and now I've got this window, which you guys can't quite see. Let me zoom in on just R. That looks like this. Yes, this is nothing that we need over there. So we'll get into some of the details about what all of this means. For now, all I need is the little command line at the bottom. So you might have your settings configured a little bit differently. Maybe yours looks black instead of white, or whatever your settings might have been. But down here, it's command line. Yeah, Stephanie.
I don't know if it's any different as I have a PC, but when I downloaded it, I've got like an RI386 and then an R times 64. Is there a difference between those two?
No, they're both the same.
They are. Okay, thank you.
Yeah, there might be different editions.
They're just different links to get to it.
Yeah, and these files are
one
like
one's a quick link, I think, and the other one's the other thing.
And it's going to depend on your system. So if you're running 64-bit versus 32-bit, 64-bit will be saved in that cross 86, whereas a 32-bit will be saved in the, backwards cross 64.
Okay, gotcha. Thank you.
yeah, and there's you also might want to watch out for like what operating system are you running on a Mac and so on, just to make sure it's compatible. So if you are having any issues getting R in RStudio installed, that's something that you and I can definitely help more individually. So if you haven't installed it yet and it's not working right now, that's okay. But if you did install it, let's just make sure that it's working properly for you. So down at the bottom is a command prompt. I can probably zoom this in quite a bit. I don't know, is that big enough for you guys to see on your screens? So, one thing I can do, not very exciting, is just say like, what is 3 times 15? So it works very much just like a regular calculator. But the calculation that we just did, what is the probability that we would get 8 good batteries out of a shipment of 10? So the command in R that's going to do this for us is what's called binom. So the binom stands for binomial. And so this is a function that is built into R. So it's going to be able to do that combinatorics calculation for us. So there's 3 things that we need to enter into this formula at minimum. So first thing is, how many successes are we trying to count? In this case, 8. We wanted to see how likely were we to get 8 good batteries. The next thing it's going to ask us for is, out of how many trials are we looking for? So in other words, what is the value of n? So in this case, we had 10 batteries in the box. And then the very last thing is, what is the probability of getting a success on any one of those trials, which for us was 99%. And then you close the parenthesis. So there's 3 things that we need to enter: how many successes, how many trials, and what's the probability of success in any one trial. And that matches up with that 0.004 that we approximated before. So if you've got R and RStudio installed, hopefully you're getting the right answer there. So with R, with distributions, there are 2 things. I'm just going to type up here so you can see it. This is definitely not R code. So when we're dealing with like a probability distribution, this is saying what is the probability of exactly 8 successes right? And that's what the formula would look like for there. So this is going to tell me what is the probability of getting exactly X successes. We've also talked about cumulative distributions. Which is called CDF. this is the probability that X is less than or equal to X. So this is the probability of getting at most X successes. So that's what the cumulative distribution tells us. And so for that one, there is also a built-in function in R that calculates those. Notice we just change the first letter from a D to a P. So if I were to come down here and run P binom 8, 10, and 0.99, so I input the same stuff, I'm going to get a very different value. How did I get, okay, well, I guess it's not that different here. It's slightly different. This is telling us how likely were we to get at most 8 good batteries in there.
How did you get that window at the top to open up, or you were able to type in the text?
Yeah, so let me just say, like, the window up top is going to be, it's used for like writing scripts. So like executing many commands at the same time. I'm just misusing it right now because I can only share one window as a way of typing stuff in there. So I'm not using it for the right reason, but to answer your question, how did it get there? I just add a new R script and it creates a blank window up there.
Okay, thanks. Cool.
Yeah. So there's definitely tons of ins and outs to R. We're gonna just scratch the very top of the surface in this class. But yeah, as we're kind of doing more and more things, we'll get more into the different aspects of this. For now, really just want to make sure like it's working as a probability calculator is all we needed to do at the moment. Okay. Any other questions before I change the screen share back to the worksheet? I think, yeah. Yeah, so one thing that's really nice about R is that it's free. And so there, you very well may come across some other software if you do some other data analysis courses that use, you know, Stata, all sorts of stuff, Minitab, MATLAB, all these other things cost money. R is totally free, and it's kind of like a community-based thing where someone writes a little script that does a really nice function like dbinom. Someone out there came up with this, and then they share it, and now you can use their function. So it's like a very much a crowdsourced programming language. Okay, so this information that we just talked about in R is over here. So how can we calculate these things using R summarized in the gray box below? And so to come back to this notion of expected value, with the previous example, the raffle ticket, we actually had to go through the calculation, and there was no like real shortcut to avoiding that calculation. With binomial distributions, we get a really nice shortcut for calculating the expected value. So if we sent out a shipment of 100 batteries, where we know that 1% of the batteries are defective, then how many good batteries would you expect to get in that shipment? Is my mic on? If we send 100 batteries, 1% of them are defective. Out of a shipment of 100 batteries, if 99% of them are good, how many good batteries should you expect to get in that shipment?
99.
Yeah, 99, right? That's exactly what it's saying. Is like 1 out of 100 is bad. So if you get a shipment of 100, you should expect 1 bad one, 99 good ones. If you had a shipment of 200 batteries, how many would you expect to be good?
198.
Yeah. Right? For every 100 batteries, you should expect 99 of them to be good, 1 of them to be bad. So in our case, we had 10 batteries. In a shipment of 10 batteries, how many of them do you think would you expect to be good?
9.9.
That's right. And
Okay.
you hesitated maybe because you're like, how can you get 0.9 of a battery?
Yeah.
And you can, right? But that's okay. These expected values are telling us on average how many good ones should we expect. So just like the raffle ticket, the expected value was 90 cents, but no one was going to win 90 cents. It was the average of how much you were going to win. Same idea here. Like there's no way you're going to get 9.9 good batteries in any one shipment. But if we averaged a bunch of shipments of 10 batteries together, on average, that's what we should expect to get.
And that has to do with us using the frequency approach to
Yeah, and
probability.
so what's the shortcut here? Do you think that we're using? So to get this 99, right, we took n times the probability of a success, right? And so for this one, we took 200 times 0.99. And so for this one, we got 10 times 0.99. So in general, we have a really nice shortcut for finding the expected value in the special case of binomial distribution. Okay, if we don't have a binomial distribution, we can't use that. We have to go and use the kind of longer way that we did the previous raffle ticket example. So in general, we should be doing this. In the special case where X is a binomial distribution, then we have a shortcut. And so on your homework, amongst other things with binomial distributions, you can definitely use R to calculate these things. I want to see your R code, not just the answer. So you can just write out what you typed into the command line in R and then show me what the output is. But you're going to have to read the questions, right? And be able to identify what is X, what is N, what is P. And you're going to have to try and identify, do I want to use D binom or do I want to use P binom or some combination of those maybe? So that's what I want to kind of practice on, making sure that when we're reading problems, we're able to identify what we need to enter into R and not worry about actually doing the calculation. R is going to do that for us. Questions so far? Okay, so on this page is a bunch of stuff that we've kind of already summarized. I should just say Bernoulli trial, this is named after a mathematician. Bernoulli is just saying it's any trial that has only one of two outcomes, a success or a failure, is what's called a Bernoulli trial. So when I said this, really it's saying each trial is a Bernoulli trial. That's a fancier word. But this is just saying if we want to use a binomial distribution, again, we have a fixed number of trials. Each trial has only two possibilities, success or failure, and it's independent of all the other trials. So here was the formula that we had already written up on the previous question. And I'll just kind of box in some of these important formulas for binomial distributions. So I would say for each of these distributions that we're going to introduce in a second, it would be good to know, like, how can you use R to calculate probabilities for that distribution? Is there a nice shortcut for calculating the expected value and the variance? And you're able to use notes during the exam. You don't need to memorize these things, but it might be nice to have them organized someplace convenient. Okay, so I think we've done a bunch with the binomial distribution. I just want to make sure that it's clear how to identify what a binomial distribution is. That was kind of the quiz. Okay. Another type of distribution is what's called a uniform distribution. And so a uniform distribution is one where every outcome, sorry. I have all of my devices here, so this is ringing on like 5 things. A uniform distribution is when all of the outcomes have an equal likely chance of occurring. So a very typical situation is like rolling a 6-sided die, which is fair. It's equally likely that the die lands on 1, 2, 3, 4, 5, or 6. And so when that happens, the probability distribution is saying, well, how many outcomes are there? If there are k different outcomes, then the probability of any one of those outcomes occurring would be 1 over k. And we've got some shortcuts for formulas for expected value and variance for a uniform distribution. Most things are not distributed uniformly. This is a really special case. So in the example of a fair 6-sided die, right, the only possibilities are that x, the outcome on the die, is a 1, 2, 3, 4, 5, or a 6. Each of those would have a 1/6 chance of occurring. You have a 0% chance of getting a number other than 1, 2, 3, 4, 5, or 6.
I have a question.
Yep.
The book made it sound like in order to meet the parameters of being a binomial distribution, that it had to have that uniform distribution throughout.
A uniform distribution would be used in a different scenario than when a binomial distribution would be used for.
Oh, okay. I must be missing something, so I'll just review. Thank you.
Yeah, no. So, yeah, binomial distributions are, we have, n trials being repeated, and the probability of a success is the same in each one of those trials. Like a uniform distribution here is just like we're rolling the die once, but each outcome has the same likelihood of occurring.
Oh, okay. I see.
And so it's possible, like if we repeat this over and over again, that you could get yourself into some sort of binomial distribution. Yeah. So what this would look like if I were drawing this distribution, we have like 1, 2, 3, 4, 5, 6. And each of these has the same probability of occurring. So it would just be, all of them would be probability of getting exactly x equals 1 would be 1/6. Probability of getting to 2 is 1/6. And so just making sure, so there's really no need to use R when you're working with a uniform distribution. The expected value here, our value for k, right, is 6 plus 1 over 2, which means you should expect to get a 3.5 on the die, right? And again, you're not going to ever on any one roll get a 3.5, but if you roll twice, you might get a 3, you might get a 4, and an average amount, you get a 3.5. And the variance would be 6 squared minus 1 over 12. So we have shortcuts in that case using a different formula. I don't know, whatever that comes out to be, 11 over 12. Sorry, that's not 11 over 12. 36 minus 1 is 35 over 12. Yeah. So just be aware there are shortcuts. Just be careful about when you're allowed to use them and not allowed to use them. This is very different than the raffle case, because for the raffle, you weren't equally likely to win $0 as you were to win $20, right? It was different for each of those. Okay, so there are a couple of others in the textbook. If you're reading in chapter 2, kind of different sections focus on different types of discrete random variables. Some of them we won't get into this year. So you're really the ones that you're responsible for working with are binomial distributions, uniform distributions, what are called geometric distributions, and Poisson distributions. And there's also like hypergeometric and other sorts of things. You're welcome to read about them. I don't think we'll see a hypergeometric distribution much this semester. So with a geometric distribution, what we're counting here are how many failures did it take before I get my very first success. So rather than saying, you know, how likely are we to get this many successes, we're saying how likely, if I'm repeating the same trial over and over again, how likely am I to get, you know, 3 failures before I get my very first success? So this would be a situation where you would want to use a geometric distribution. Okay, whereas a binomial distribution is saying how likely are we to get 8 successes out of 10 tries. This might be saying how likely is it that the first 3 batteries are bad and the first good battery we get is the 4th battery in the shipment, for example. So this formula is actually much easier to use than the binomial distribution formula, but you can use it in R if you want. Let's kind of just think about this example below, though it's sad to think that these days nobody's going to any sporting events, but there was a time when that did happen. And so here, let's think about, you know, we want to calculate how many people are going to Nuggets games in Denver. And so there's Marker that works for the Nuggets, and based on some data, they know that maybe 10% of the population did go to a Nuggets game last season. So we're going to assume, like, the trial here is you call a random person in Denver and you ask them, did you go to a Nuggets game last year? And the probability that that person says yes is 10%. The probability that that person says no is 90%. And then you call the next person, and those odds are all the same regardless of what the person you just called said, right? So that's why this would be a binomial distribution. We're repeating the same event, calling people, where the odds of them going to the game is the same 10%. So the question is, okay, what is the probability that they get 7 people who did not attend the game before the very first person says yes? So here, what we're trying to calculate, what is the probability that X is equal to 7, meaning we get exactly 7 failures in a row before we get our first success. So the outcome here would be fail, 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 fail. 1, 2, 3, 4, 5, 6, 7, And then the first person says, yes, I did attend the game. So the ordering is very important when we're thinking about these geometric distributions. So if I wanted to calculate this probability, I would just say, what is the probability of a failure, right? And we often denote that with a Q. And we have 7 of them times, right, the probability of this very last one being a success. So it's going to be 7 failures in a row. What's the probability that that would happen times the 8th one finally being a success? So in this case, the failure, they didn't go to a game last season, would be 0.9, 0.9, 0.9. So we want to get 7 of those people in a row before the 8th person says, yes, I did go to a game. And so that's where this formula comes from up here. So if you want to calculate the probability of X failures before the very first success, you take Q, probability of a failure, raise it to the X power, and then multiply by the probability of a success. And R does this very similarly. So if I wanted to calculate this particular example, I could certainly just do like I can ask it to actually do the calculation, take 0.9, raise it to the 7th power, and then multiply by 0.1. Or we can say, what is the probability of getting exactly 7 failures before the first success? And R will calculate that all at once. So when you're doing the DG ohm, let me come back to the, there's only 2 things you enter in there, which is how many failures, what is the value of X, what is the probability of a success. We don't have a fixed number of trials here. There is no N. We don't know how many people we're going to call. There's no set limit to that. Okay, any questions? Okay, and then one more distribution to talk about, and we can start class next time taking a look at some of these examples on the last page, identifying when to use them and how to use them, would be what's called Poisson distribution. This is named after a French mathematician, Poisson. And so this occurs when we're in the situation where we know, like, on average, how many times does a certain thing occur in a fixed set amount of time. So for example, if we're counting like how many cars go over a bridge in an hour or whatever in a minute, we might ask ourselves, you know, how likely is it that 4 cars drive over this bridge in the next minute? And so, sorry, my dog is barking in her sleep behind me. So in a case like this, there's one parameter in this distribution, which is this letter, excuse me. Let me get back to my screen, sorry. Can you guys hear anything in the background? Okay, that there's one parameter in this distribution, and that's denoted with a lambda. we go. And this lambda tells us, you know, on average, how many times does this event occur in a fixed set period of time? Yeah, sorry, we're out of time. So I'll stop here. We'll pick up with the Poisson distribution next time and practice a couple of these at the end. Yeah, and then we'll get into continuous distributions a little bit. So the continuous distributions are not on your homework, which is due on Monday. It'll just be on the discrete stuff. So kind of the video that I'm going to ask you guys to watch before class on Wednesday is going to set the stage for the continuous distributions a little bit. That's what the quiz will be on. But we'll wrap up these last couple of examples with the discrete distributions before we begin that. So I think it would be good for you guys to start taking a look at the homework, since these practice problems are very similar to those. And you know, at least if you have an idea of what stuff makes sense, what stuff doesn't make sense on the homework, we can kind of focus on those things while we practice these problems on Wednesday. But if you have any questions in the meantime, getting your homework going, you has got office hours, I think, later today, 4 to 5. Is that right, Yua?
I think that's tomorrow.
Oh, tomorrow.
At 4 p.m.
Okay, so Tuesdays, 4 to 5. I've got office hours tomorrow from, let me check my schedule. It's either 1:30 or 2. I think it's 1:30 to 2:30 tomorrow for myself. So yeah, so feel free to stop by office hours, 1:30, 2:30, 4 to 5 tomorrow. Otherwise, I'll see you guys all on Wednesday.